Hi there. Today we would like to take a look at barrier optimization in LimaQ. So what is barrier optimization about? When we create a noise barrier, we usually do so because we want to reduce the noise levels at a certain receiver point. And we could go about by doing it in a trial and error way, starting with a barrier height at, let's say, 10 meters, then have a look if the levels that we want to reach with this barrier are already there, and if not, then make it a bit higher, and so on. So this could be a very long and tedious process, and what it could also end up with is a barrier that is way too high for the result that you want to achieve. So in LimaQ, you can let LiMA do the calculation, and all you have to do is define some receiver points with a location and the noise levels that you want to achieve. And you also have to describe the barrier footprint, where the barrier is to be constructed. And then you can let LiMA do the calculation, and it will come up with a solution that is basically the minimum height of the barrier to achieve the output that you want to achieve. And so what you do is when you create the barrier, you not only create one line where the barrier is supposed to be, but you also create segments. So because LiMA can only optimize the one segment at a time, and if you create only one segment for the whole wall, then you will have one wall with a uniform height. You can do that, but in our case we are going to show you how you can even optimize this process by creating different segments. So let's take a look at our model here. We have a small village next to a 4-lane highway. And in our model, we have the village represented by a obstacle file or obstacle object. And the 4-lane highway, we have for the whole 4-lane highway, we have digitized a road object with 2 lines representing 2 lanes each, with a constant noise output of 70 decibel. And to have an idea what the noise situation looks like, we have already calculated a raster noise map. And here you can see that first of all, I mean, it's a very loud road, and second, the buildings closest to the highway are affected in the most severe way. If we look at the levels at these buildings close to the highway, we are talking about noise levels of between 55 and 60 decibels. So what we want to do now is first create a footprint of our noise barrier that goes along the eastern side of the highway, and then we're going to define a few receiver points at the buildings that are most exposed, and that's basically it. Then we're going to tell LiMA to do the calculation, and it will come up with a optimized barrier. Okay, so let's get started. Okay, so let's get started with the digitizing of the barrier footprint. We have to create a new LiMA layer for this, so go to the LimaQ toolbar and click on the new LiMA layer button, and then select obstacle as object type. In our case, the geometry type is polyline, and then select the coordinate reference system of your project and save the file in your project folder. Before you start digitizing, I recommend to check the styling of your new layer. I'd like to make sure that the color is well contrasting to the background, and for polylines I usually increase the line width also. And then you can start editing, click on the toggle editing pencil and create a new polyline, and then put the first vertex on the canvas where you want the barrier footprint to start. And what you see here on the left is the advanced digitizing toolbar, which is a really useful tool for these kinds of tasks where you want to create segments that have the same distance. What you do, you click on the first vertex, then type in the distance that you want to digitize, and then press enter, and then it constructs a circle around the first vertex with the distance that you've specified, and so you can make sure that you always digitize the same distance. Okay, so then you repeat the process for all of the segments that you want to create, and don't worry about the attributes that you're asked to change or specify after each segment. We leave them as they are for now, and once you've finished the digitization, you will save the objects and then go to the attribute table, and then we're going to change the attributes altogether. So now we've finished. We go to the attribute table, and the column that's interesting for us now is the obstacle column. And the numbers or figures that you see me fill in here are the identifier for each segment and the minimum and maximum value for each segment. So in our case, we want all the segments to be between 0 and 15 meters high, and additionally the first number we enter after the /SSG, this is the identifier for each segment. So we repeat this process for each segment, so that each segment has its identifier. And then once we've done that for all of the objects or segments, we can save the file. And that's basically it. Now we finished the barrier and we can go on to the receptor points. Okay, before we put our receiver points somewhere, I want to make sure that I know which houses are most exposed to the noise from this highway. So I turn back on the noise map that I already calculated, and here I get a good idea which are the houses most exposed and which are going to be the places where I'm going to put the receiver points. So I'm going to create a new LiMA layer. It's a receptor layer, and the coordinate reference system again is the one of your project, and I'm saving it in our project folder. And again, I changed the style so that I can see the receivers properly once digitized. And now I can start putting the receivers on the facades. So I put the receiver, one receiver I will put here. I leave the settings as they are for now and come back later. Then maybe I'm going to put another one around here. And another one up here. Okay, I save it. And then I open the attribute table. So the attribute that we have to change here is the AUF receptor attribute, and what we put in for each receptor is first an identifier and then the maximum noise levels according to your standard. In our case, we have 3 values for day, night and evening. And so for day we have a maximum value of 59 decibels, and for the evening and the night we have 49. And we can copy and paste this into the other receptor lines, and then we just have to change the identifier. Okay, then we take a quick look at the other attributes here. One that might be interesting for you is the distance to the facade. In our case, it's 0.5 meters, and the Z value. So this attribute Z value specifies at which heights LiMA is going to construct the receptor points, and what we see here, what this specification means, that the first receiver point will be placed at a height of 2.8 meters, and then it will place more receiver points every 3 meters up to a height of 10 meters. Okay, so we can save this now. And now we've created the receiver points. Okay, so now we are ready to start the calculation. Before we click on the road traffic noise symbol in the LimaQ taskbar, make sure that the canvas covers the whole extent of your model. In the road noise calculation interface, give your project a name. Make sure that all your model files are included in the model. Define signal points as the type of receptor point, and check optimization of barriers. In the options menu, make sure that you use a default value of ground level in case that you have not included a terrain model in the model, and also check that the emission attributes match those specified in your emission object, in our case the road object. Okay, then click accept and start the calculation. In case you haven't started the server yet, you'll be asked to do so. Also check server record on screen to have some feedback what's happening during the process. And you can also call the LiMA taskbar or the LimaQ interface to see where you're at with your processing. Okay, once you hear that noise, it means that your calculation has finished. And now we can open the new barrier from our project folder. So click on import LiMA model, and then what we want to open is the conbna file, and this will open all the parts of the model, including the new optimized barrier. For each of the files you have to specify the coordinate reference system, and then we can take a look at the optimized barrier. And in the Z attribute column we can now see the different barrier heights that represent the optimal barrier geometry. Okay, so that's the result, and now we are going to show you how to visualize these results. Okay, so what we want to do now is to visualize the results of the newly optimized barrier in a 3D viewer. To do that, we first have to change some attributes in the new barrier file that we took from the conbna. And when we look at the attribute table at the Z height, we see that the formatting is a bit particular to how LiMA is working and not so easily digestible with other plugins. So in order to make this work for our 3D viewer, we have to create a new attribute where we only see one of the heights. So we first start editing and then open the field calculator, and then we create a new field and we name it ZOP. We create it as a decimal number, and then we extract the values that we need from our original Z attribute by typing substring. Schalt dich nie mal auf, hörst du das nicht?
Nein. Nein, wenn ich das gehört hätte, würde ich ja nicht kommen.
Okay, raus, ich mache das jetzt fertig hier an, das dauert noch 2 Minuten. Okay, so we create a new field. So we create a new field. We give it a name, let's say ZOP. Define it as a decimal number. And then we extract the first two values of our Z field by writing substring. Then from the Z field, from position 1 with a length of 2. And here we already see what the preview would look like. And then we tap OK. And then our program stops working. So what we want to do now is to visualize our new optimized barrier in a 3D viewer. To do that, we take the extracted new barrier from the conbna file and export it as a normal shapefile. We give it a name. Make sure that the Z dimension is included during the export. Click OK. And now we can delete the older file. And now we go to the attribute table. And what we see here again is the Z height attribute, which has a format which is a bit particular to the LiMA LiMA program, and so we have to reformat this one here to make it digestible for the 3D viewer. So we go, first of all, we start the toggle editing, then we open the field calculator and we create a new field called ZOP. We define it as a decimal number, and then we extract the first two values from our Z-height column. We do that by writing substring, then we select the Z column. We want to extract the first position from the first position starting 2 positions, and down here we see what the result would look like. That's good. And now we click OK. And now here you can see the newly updated field. Okay, so now that we have reformatted the Z value, we can save the file and open the 3D viewer. Go to Web and select QGIS to 3JS. And now take a look at the model. So we can see here that our barrier has different heights. So at the lower end, I think this will be probably the 5-meter section, and then the highest section somewhere around here. Okay, that's it. And in the 3D view you can have all kinds of fancy visualizations to present your result, but I think that looks already pretty good. Okay, that's it for today. Thank you for watching and see you next time.